Welcome back to the deep dive. Today, our mission, well, it's laser focused. We want to give you the real operational and theoretical structure of aircraft computer systems.
Exactly. And if you're getting ready for those ATPL exams, this is really for you.
We're aiming to distill that core knowledge, the definitions, the crucial distinctions, the applications, basically, everything you need to nail those questions.
Consider this your shortcut to understanding the technological brain of modern aircraft. How it works, why it's built the way it is.
We're building this deep dive using insights from basic computers and aircraft systems.
It's all about synthesizing complex stuff quickly, focusing on what examiners look for, like understanding memory types or why software safety levels are so vital.
Okay, so before we jump into the deeper stuff, let's lay down the simplest foundation. In this context, what is a computer?
Right. At its absolute core, a computer is just a device, or maybe a set of devices that can do fundamental things.
Which are?
It can store data. And crucially, it can store a program that's the set of instructions that operates on that data.
Data and program, that duality.
That's the constant. It applies to everything from the tiniest chip right up to a complex flight management system. It's always about the data and the instructions acting on it.
And just to give that some historical context, because it goes back further than you might think.
Oh, absolutely. The core idea, using binary, that two-state system, zeros and ones, was actually proven functional way back.
We're talking Konrad Zuse, Germany, 1941, the Z3.
Exactly, the Z3, the first fully operational general-purpose computer. Now, it wasn't silicon like today, it's electromechanical. Used relays.
Clunky compared to now, I imagine.
Definitely. But the genius was its use of binary digits. That fundamental two-state principle, on-air, O-off, 0 or 1, that's been the bedrock for, over 80 years now?
Okay, so when we're analyzing computer systems, especially thinking about ATPL theory, the very first big distinction you absolutely have to get straight is analog versus digital.
Couldn't agree more. That's fundamental.
Let's start with analog. What defines an analog computer?
An analog computer is all about how it represents things. It uses continuous physical variables.
Continuous meaning?
Meaning things that vary smoothly without jumps. Think voltage that ramps up, air pressure that builds gradually, maybe rotational speed. It represents and manipulates real-world measurements directly using these continuous signals.
The output mirrors the input smoothly.
Precisely. Hence, continuous. And historically, these were incredibly important, especially in early engineering.
Right, for things like aircraft design.
Exactly. They were basically electronic models, analogs of complex mechanical systems.
So instead of building a physical wing prototype,
which would be hugely expensive and take forever,
yeah.
You'd build an electronic analog. You could feed in simulated inputs like changing air pressures of varying voltage.
And the computer would show how the wing structure might react.
It would show how the system responds dynamically, using those continuous voltage changes. It let engineers predict motion, stress, flutter, all sorts of things, without ever leaving the lab. Super useful for bridges, control systems, you name it.
But obviously we don't see many dedicated analog computers around anymore. Why did digital take over so completely?
Well, analog systems have limitations. Precision is one. They're great for showing dynamic relationships, but they can suffer from electrical noise, drift in components over time, and just the physical limits of accurately representing a variable with voltage or pressure.
So accuracy issues.
Accuracy and complexity, yes. As digital computers got faster, cheaper, and much, much more power.
Exponentially so.
Right. They could be programmed to simulate those same moving physical systems, but with far greater accuracy, repeatability, and without the drift issues. So, dedicated analog machines for design. They're pretty much obsolete now, replaced by digital simulation software.
Okay, which brings us neatly to the cornerstone of all modern aviation tech, the digital computer. What's the absolute non-negotiable defining feature here? This is critical for exams.
The data type. That's it. Digital computers use digital data, and digital data is basically binary.
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best